We discussed up to Bateman's rearrangement. Fifth reaction, we'll see. Reaction with alcohols. Now, if you take any aldehyde and treat that with alcohols, let's say I take 2 moles of R-OH. And this reaction is feasible only if you have it in dry HCl. Then we will get this as RCHOR-OR- okay, plus H2O. Now, if you notice, this reaction is feasible more in the forward direction only if you use dry HCl. If you use aqueous HCl, reaction would immediately come back, which means step by step, if you notice, C double bond of H, first protonation will take place. This will convert into CO plus here H, and then R-OH as a nucleophile will attack here, and we will get a compound like this, which is OH and OR, which we call it as hemiacetal. And then, if you make this reaction further with H plus, the lone pair will again attack here, converts into OH2 plus with OR, and the next mole OR dash here. The second mole of this molecule will come and attack so that this water molecule can be relieved, and we get OR dash and OR dash. What is this one? Acetal. Okay. So we shall get acetal and hemiacetal in this case. Got it? Acetals are unstable even in the basic medium, but hemiacetals are unstable in basic medium as well as acidic medium, while acetals are stable in basic medium. So we need to remember that hemiacetals are unstable in both acidic and basic medium, while acetals are stable in basic medium. Now, by chance, if you try to make ketones to work on it, that is R-OH of 2 moles by using dry HCl to get acetal here, OR dash and OR dash plus H2O. The problem what happens here is one thing, ketones are very less reactive towards nucleophile addition. Second thing, once you get this is huge crowded, and again it will immediately hydrolyze and come back. So reaction feasibility is very low here. Okay, delta H is closer to positive or zero for this reaction. So to improve on this spontaneity, instead of taking 2 moles of alcohols, we'll take only 1 mole of alcohol, which is in the form of a diol. Then the reaction will proceed. Dry HCl. In that case, the reaction will proceed now to form this kind of cyclic acetal. Cyclic acetal form plus H2. Okay. Now this reaction is feasible. The first reaction is not so much feasible. Correct? That's why typically, suppose I have double bond O here and double bond O here, and when I treat this with OH, the presence of dry HCl of one equivalent, then one of the locations will get locked. This is called locking the carbonyl group, and the other group is open. So from here, if you treat with lithium aluminum hydride or sodium boron hydride, okay, sodium boron hydride here, or zinc Hg and HCl this time. So you know that respectively, without disturbing this group, we will get, sorry, not this one, NH2, 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 NH2 in the presence of KOH. Then this hemiacetal, the cyclic acetal will remain, and the open carbonyl compound will get reduced. So this will be the product form. And on the other hand, second case, you know that it is Wolff-Kishner reduction. In base medium, cyclic acetals are stable. So this is the product form. And then on further hydrolysis, acidic hydrolysis, this double bond O will come back. Similarly, here also H3O plus, this double bond O will come back, but this got reduced. So you can see these positions got reduced. This is typically how we do the locking of acetal groups or carbonyl groups, and based on that, we will perform the reductions. Clear? I hope all of you understood this logic. Right. Now, let's see today what are the tautomeric reactions. Got it? And how that will influence haloform, aldol, and all those reactions. So first, let us go and discuss about tautomerism. Typically, when it comes to tautomerism, the basic things which we need to know is this, that when you have an ketone, it will be in equilibrium with enol. Ketone and enol will be in equilibrium. And if this is K equilibrium, we know that for various groups, okay, the enol content, percentage enol content is decided based upon K equilibrium. If K equilibrium is greater than 1, then enol content is more. Enol content is more. Okay. What you would notice is that, you know, enol content depends upon stabilizing factors. If there are any stabilizing factors, then enol will be more stable. And percentage enol, okay, close to 100, close to 100% is observed when you have phenol here, when you have double bond O, double bond with phenyl here, when you have it in the cyclic structure with double bond O and double bond. Here we'll have percentage enol to be 100%. Okay. Well, this is the enol I have written. Let me write down the keto part of it. This one. If I write the keto part of it, the respective enol for this one, respective enol for this one, and enol for this one, they'll be almost close to 100%. Okay. Like this, any stabilizing factors, if you notice, they'll be 100%. Okay. And anything which is greater than 50%, okay, enol percentage, which is greater than 50%, greater than 50%, anyways, these three will be there. Along with that, anything which has, only hydrogen, that will be slightly more than 1 methyl, slightly more than 2 methyls, slightly more than 1 methyl with 1 ester, and then both sides we will have esters. This is approximately 8%, and this is close to 10 raised to power of minus 4%. Okay, so you can see otherwise these three are sufficiently high percentage, much greater than 50 percentage. So all of these are greater than 50 percentage, greater than 50%. If you notice the tautomerism happens better in basic medium compared to acidic medium. So that important note we need to check, that tautomerism is tautomerism is more easily observed in basic medium than acidic medium. Basic medium than acidic medium. Now, using that, what we could discuss is first kinetic isotopic effect, kinetic isotopic effect due to tautomerism. Well, you see, due to tautomerism, if you have double bond O here and I treat with NaOD in the presence of D2, in that case, wherever there are hydrogens, there the deuterium exchange will happen. May not instantly, in prolonged time. Prolonged time, we will see this reaction will take place. Okay. And like that, if at all I give you a compound, you should know how many deuterium exchanges will happen. For this compound, check out how many we will able to see. Okay. If I write the same thing in the form of phenol, how many deuterium exchanges we will have? If you have double bond O and like this, then how many deuterium exchanges we will have? Double bond O and double bond O, how many deuterium exchanges we can see? If you have this way, then how many deuterium exchanges we will observe? Check everybody. So I'll copy all of them. You need to check out the positions where we have kept this. Now, notice here exactly we can get. First, I can get minus charge here by removing one hydrogen, which means here whatever the hydrogens are, they'll be exchanged by deuterium. And then that minus charge can also come here due to resonance. So there also I'll make a deuterium exchange. And left hand side, this side is also alpha hydrogens. And all alpha position hydrogens are also going to get replaced by deuterium. So for this example, how many we will have? 5 exchanges will be observed. Next, here you can see these two. These two will get deuterium exchange. Due to resonance, this one will also get deuterium exchange. And here also it will get deuterium exchange. So 4. Similarly, if you notice for phenol also, in case of phenol, if I write the enol form of it, enol form of it is like this, double bond O, like this way, or I can write double bond O with this way and this way. Okay. In either cases, wherever there are hydrogens here, 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 and here, except for the meta position, all those positions will be exchanged by deuterium. So therefore, here there is one deuterium exchange, here, here, and here. These are the locations where the deuterium exchange is observed. See next, here there is a keto group. So all of these positions will be deuterium exchange. This is at alpha position. And these three are also going to get deuterium exchange. And here, whatever deuterium is, that will also get exchanged. Similarly, here we can get two deuterium exchanges. Here we can get three deuterium exchanges, and here we can get three. And in the last case, no deuterium exchange because there is no tautomerism. So no tautomerism, no deuterium exchange. So keep this in mind. When there is no tautomerism, there is no deuterium exchange observed. Got it? Now this is the basis which we expect to know. Okay, based on that, we can develop the other cases. Let's see. Now, let us discuss about Cannizzaro and aldol reactions. Start with Cannizaro's reaction. Condition is it is only for aldehydes. Okay, only for aldehydes. Okay, with no alpha hydrogen present. Second, undergoes disproportionation. Undergoes disproportionation reaction. Okay, and third is high concentration is required. High concentration of base NaOH or KOH greater than 50% concentration is required. Okay. Now, what is the reaction here? I'll show it with an example. So, if I take 2 moles of an aldehyde, formaldehyde, taking 50% of NaOH, then we shall get this as HCO minus Na plus, and second mole will become CH3OH. So, one will become alcohol, the other one will become acid. And if I take 2 moles of PHCHO, same case, if I take 50% NaOH, then we will get PHCO minus Na plus plus PHCH2OH. PHCH2OH. So this is how the Cannizzaro works. Mechanism wise, if we take HC double bond OH, the OH minus as a base is attacking here. So that will make HCO minus OH and H. Okay. Now once you get this H, due to the strong plus psi effect, from O minus, right? We will be able to remove this H minus also. So if I take the second mole of it, then this pi bond will push here and this hydrogen will come out as H minus and attack here. And this will be the rate determining step. So which makes HC double bond OH of 1 mole. The other mole will become CH3O minus, which will consume this H plus and finally converts into HCO minus plus CH3OH. This is in forward direction. So that's how you will get the product as one getting disproportionated. 1 mole of the carbon is converting from this position to this one, which is oxidation. From here to here, it is getting reduction. So one gets oxidized, the other one will get reduced. Okay. So if you notice the rate of reaction will be some constant into HCHO whole square into OH minus. So it is a third order reaction. And since hydrogen exchange is happening, so and that too happening in the rate determining step, primary isotopic effect is observed. Primary isotopic effect observed. So if we compare the rate for hydrogen, it will be more than deuterium than tritium. Okay. Now, if we have above 50%, above 50% NaOH, correct, or high concentration, then multiple steps will happen. That means this molecule HCO minus OH and H which has formed reacts again with OH minus, extract this H plus, converts into O minus and H. So this way, now O minus is even strongly donating from both ends. And now in the second mole, this bond will close and this will become H minus and that will attack. Again, this is the rate determining step. So we will get this as HCO minus directly and CH3O minus. Okay. This time, if you notice the rate will be equal to constant into HCOOH whole square into OH minus whole square. So order of the reaction now will be 4. So it is fourth order reaction in this case. Got it? Just go through it once again, everybody. If you have a doubt, let me know. So the fan. Done. Now see, we can make Canizero as self as well as crossed, intramolecular, and so many different types we have. I'm sure you got an idea about these cases. So directly, let us see with the examples. So if you have benzaldehyde and that I'm treating with formaldehyde with, you know, 50% NaOH. In such case, you will notice that formaldehyde will get oxidized and benzaldehyde will get reduced. So between when it comes to cross conjugation, whichever is most reactive aldehyde, that should always undergo oxidation. So here formaldehyde is more reactive than benzaldehyde. Therefore, this will undergo always oxidation. And which is less reactive, that will always undergo reduction. Okay. So that way we need to judge. Got it? Now, if you notice few exceptional cases, in which cases Canizero is possible and not, let me check out. As an example, which cases Canizero is observed. So, for example, if I take benzene with nitrogen having two methyl groups here and CHO. Now, this nitrogen is so much strongly donating this forming an enolate ion, right? It becomes very, very challenging. So that's why cancer is not observed here. Got it? At the same time, if you have CH and CHO, and if I take concentrated NaOH, in this case, CanZero is observed, although they have a alpha hydrogen. So this is one of those exceptional cases where despite having alpha hydrogen, CanZero will occur. Okay. In this case, no CanZero will take place. Now, anything of this sort where we have, chlorine present, let's say, chlorine is present, definitely it will go CanZero. If we have only NO2 present, let's say, In this case, I have NO2. Here, definitely Canizero will take place. Got it? So, these are those cases where you will see Canizero can happen. Okay. In all other cases, you know that if you have CHO here, definitely here Canizero will happen. If you have any double bonded carbon here, double bond O like this with H, here also Canizero will happen. So as long as there is no available alpha hydrogen or any hydrogen which can undergo tautomerism, if that is not there, definitely we can see Canizero cases will be observed. Okay, next. Suppose if the question is given like this, what if you have an keto form here with OH minus? Okay, here no aldol will take place. Okay, although we have an alpha hydrogen here because the double bond inside the ring is highly unstable. So instead, the reaction in such cases will not be either aldol or canizero. Simply this OH minus will attack here to open this ring. So ring opening would be observed. So we will see minus charge coming here and OH attacking here, and this will become double bond O. Okay, this is how the ring opening would take place. Okay, so I hope all of you got an idea. Now, I'll give you some cases. I want you to write down the products in the Canizero case first. Example 1, 2 moles of HC double bond OD if you treat with concentrated NaOH. Write the products, okay? Everybody practice this. HC double bond OH when you treat with NaOD. Next, HCHO plus CHO in the presence of NaOD. Next, CHO NO2 plus here benzaldehyde only in the presence of NaOH. Check out what are the products we are getting. Next, PHCH2CHO plus 3 moles of HCHO. Then what do we get? NaOH. Check out in all these cases what are the products formed. And lastly, if you have CH3CHO plus 4 moles of HCHO. So this is one equivalent, this is 4 equivalents. In the presence of OH minus, what will happen? Right. Let us quickly go through one by one. First case, between deuterium and hydrogen, always hydrogen will get exchanged. Deuterium will remain. So we will have D, C double bond O, O minus, and this H will get exchanged to the other molecule. So we'll get this as C, H2D, and OH. Now, mind you, this hydrogen will come from this one. Okay, from whatever the OH that we have added. Clear? Next, NaOD. So what do we have here now? So first H, C double bond O, O minus, this will form, and then The second mole which is getting reduced will have CH3OD. That is a product form. Again, this D will come from here. Next one. Between these two, this will in cross Cannizzaro always the more reactive part will get oxidized. So I'll get HCOO minus plus this will become CH2OD. Again, between these two, the more reactive is nitrogen, NO2. So that will become acid. So we will get COOH, I mean CO minus NO2, and this part of aldehyde will get uh, reduced to alcohol. Next. Now, what if you have 3 moles? I have to perform the cross Cannizzaro, but I have to do 3 moles. But for that, here is catchy part. Whenever you have CHO, along with that there is alpha hydrogen present at the adjacent carbon, you always start with aldol first. Now what exactly happens in aldol? This OH minus will first take away this H plus, creates a minus charge on it, and that minus charge will go attack on this aldehyde. So in that case, what do we get? PH, CH, and I'll put this CH on the other side. This will connect to CH2O minus. Okay, this is the first mole attack. If you do the second mole again, right, and once you get this attack, after that hydrolysis will happen, you'll get OH here. Now, when the second mole attacks, again this hydrogen will be exchanged here. No, so we'll have PH, and now we have CH2OH and CHO, and this side again I'll get to attack on aldehyde to get alcohol. So 2 moles of this alcohols are formed, one aldehyde is present. Now you would see there is no alpha hydrogen. So now this time when you go for a third mole with HCHO, here we will notice only Cannizzaro happens. Now we'll see only Cannizzaro happening. So if there is only Cannizzaro, obviously aldehyde is formaldehyde is much more reactive than the given compound. So this will get reduced. So we will get OH, OH, and OH. This is the product form. Plus, now this compound will undergo oxidation. So that becomes HCOO minus. So that is a product form. If you do the same thing for the next case here, this is called Tollens reaction. It's called Tollens reaction. So if you do the same thing for Tollens reaction, you will notice that we will get CH3, sorry, every time we are removing one hydrogen here, adding one swastik kind of group. So CH2, CHO with one OH. This is first mole. Then CHO. Then we have OH and OH. This is the second mole. And then the third mole, OH, OH, and OH with CHO. And the last mole will be about OH. And this last step will be about Cannizzaro. Last one what we get is of Cannizzaro. Plus that 1 mole extra we will have is HCO minus. This is Tollens reaction. Okay. Check, anybody has a doubt, they can ask. Next. Check out these questions. Suppose if it is given CCl3CHO and treated with OH minus, then what is the product we will get? Similarly, if you have CHO, CHO and CH3 here, and then OH minus has been attack. Then where will the reaction happen? And NO2, CHO, and CHO. Where does the Canizero happen? What is the product you will get? Then I'll have two different molecules. One is CHO with Cl, CHO with methyl. Combining these two, what is the product form? Okay, and this is called furfural, which is CHO, furfural. If you treat with NaOH, 2 moles of this, what do we get? Okay. Lastly, if you have CHO with NO2 here, NO2 here, and NO2 here, I took 2 moles of this in the presence of OH minus, then what is the product form? So try these questions quickly. Notice the first case. In the first case, what you will see, because CCl3 is a very good leaving group, as soon as the OH minus attacks here, CCl3 minus will go and not the hydride shift. So hydride shift is not happening here. So we will see CH, Cl3 will form, chloroform, and HCO minus Na plus. So remember, no Canizero. Okay. So I will add this also to the list here when we wrote that. So you can see CCl3, CHO. No Canizero in this case. Okay. Second one. Between the positions here, if at all you identify the position, between this one and this one, methyl is going to give more donating nature to this CHO. So this CHO is less reactive and this CHO is more reactive. And whichever is more reactive will become acid. So we will see this as CO minus and this will become CH2OH. So this is intramolecular canism. Same way here if you notice, this will become alcohol and this will become acid because now NO2 is withdrawing. That will make that CHO, first CHO more reactive. Here, chlorine containing group is more reactive. So that will become acid and methyl containing group will become alcohol. So CH2OH with methyl group. Next, this is furfural. Furfural 2 moles will give us CH2OH and one will become acid, CO minus. Lastly, now if you notice this NO2, if there are so many NO2s around CHO, it becomes difficult for it to react. So first OH minus will attack. As soon as the OH minus will attack, now this bond instead of hydride shift, this benzene only will come out. So we'll get minus here, NO2 here, NO2 here, and NO2 here. And the rest of the carbon will become HCOO minus. Okay, so that will become HCO minus. I guess this is clear. So after adding water, what is the product we will have? The products will be this benzene with 3 NO2 groups. It will take one H plus from water and HCO minus will also take and converts into an acid. These are the final products formed. Okay. So I have exhausted all the cases of Canizero. So I hope you guys understood how to work around Canizero cases. One more case. Yes, Vito.
Can I explain last step once more?
Okay. Check here. C double bond OH. We have NO2 and NO2. OH minus is attacked. As soon as the OH minus attacks here, we will get CH, O minus and OH, and here I have NO2 and NO2. So instead of H minus coming out, as soon as this bond closes, this bond will break onto the other side. Okay. So you will directly get this intermediate and this will convert into an acid. Clear now?
Okay.
Right. Next, let us see the other applications of Canizero, which are very similar to Canizero. One of them is Tischenko. Honestly, Tischenko is not in the syllabus, but by chance, if we observe a reaction like that, how do we respond? Let us understand. So usually happens with any aldehyde. So it is not necessary we need to have any issue with the alpha hydrogen, nothing of that sort. Only thing it reacts with aluminium ethoxide, okay, ethoxy, triethoxy aluminium. Okay. In that case, we will see it will become ester. So CH3, COO, C2H5. This is the product form. All you need to do is think in terms of Canizero and make a reaction. That is, if you have these two reactions happening, these two aldehydes reacting, what do we do in Canizero? In Canizero, we know that one we will make an acid, the other one will make it as an alcohol. Now, imagine as if you are doing esterification of these two. Okay, this is esterification. Esterification of this. That's how we will get an ester form. Okay. This is easy to remember. See how the questions are being framed. Let me give you one or two examples here. Double bond OH, double bond OH, and suddenly if you notice that there is an aluminum based epoxide or anything like that, any alkoxide like this, then one side you make an acid, one side you make an alcohol first. That's an easy way of trying. Here I'll have this as an alcohol and this side I'll have this as an acid. Then make an intramolecular acid-base reaction. I mean, you make an esterification and this is the product form. So this is about Tischenko. Next one is, the next application is benzylic acid. Benzylic acid rearrangement. How does this work? See, pH C double bond O, C double bond O pH. This is what we call it as benzene. And benzene, if we treat this with OH minus followed by hydrolysis, then we notice it forms OH, pH, and COOH. So exactly every step that happens is similar to that of Canizero here, except of hydride shift. Now we have a phenyl shift. That's the only difference here. So that is pH, C double bond O, C double bond O, and pH is there. You take OH minus attack here, O minus will come. So we will get C double bond O, CO minus, OH here, and phenyl will come. So as soon as this closes, now the phenyl will start shifting. Internally, phenyl will start shifting. So we will get this as O minus, pH, and COOH. which this will take pH to get OH and pH with CO minus. Done. This is how the benzyl benzalic rearrangement is observed. Okay. Where do you see these typical examples? Okay. We in this area, it's very important to decode the examples. Okay. So if this is how it is given, and then there is a double bond O and double bond O given, and this is also connected to a furfural here. This is a furfural, and if this first reacts with NaOH and then followed by hydrolysis, okay. In that case, what do? We will make sure that this furfural will exchange on one side. So we will get 2 moles of furfural, this one connected to another furfural here, like this, and that part will become alcohol and the other part will become acid, like this. This is the product form. Okay. Next, another example you will see is this one. And suppose if we have two benzenes, two phenyl rings connected like this, and we will have double bond O and double bond O here. Okay. And then again, if I treat with NaOH followed by H3O plus. Now, this time you would notice that this entire group will start shifting. So that 5-member ring will become a 6-member will become a 5-member ring. This way we will have, and this will convert into a 5-member ring here. Okay. Like this, with one having OH, the other carbon becoming COOH. So this is the final product which is formed. Next, the next mechanism, which is of a similar applications of that of Canizero, is benzoin condensation. Benzoin condensation. Okay. Observed only with benzaldehyde. So if you take benzaldehyde, you react this in the presence of NaCN or KCl. Then we will see pH, CH. We will see this as O minus and cyanide. And here IMPT will happen. Okay, where this hydride will shift onto the oxygen, because that hydrogen is very acidic now because of the cyanide group. So we will have this as OH cyanide with minus charge on it. Okay, which I can say can be observed in the form of pH COH double bond C double bond N minus. This resonating structure will help it to form that. Now this molecule will be attacking on the second mole of it. So we take this attack on the second mole, that is pH C double bond OH. This minus will go attack here. This will rearrange and we will get pH COH with cyanide connected with CH and O minus. And again here will happen where hydrogen will be moving from this oxygen. Cyanide will be here, CH, OH will be here, and phenol. And this will close to remove the Cl minus, Cn minus. So from there we will C double bond, CH, OH, and phenol. Okay. Sorry guys, one second. I lost the connection. Let me reconnect. Done. Okay, let us see about aldol now. If there is any issue coming again, I'll come to the class and discuss. Okay. So for now, let us try for completing the aldol. See, aldol also has a lot of cases which includes self-aldol. So between the two molecules itself, so if you have 2 moles of CH3CHO in the presence of OH minus, we will get this as CH3CHOH, CH2 and CH. Okay. And this is what we call it as beta hydroxy aldehyde, beta hydroxy aldehyde. We call it as aldol. And usually on heating via even CB mechanism, we will get to see this as CH3 C double bond O CH, sorry, CH3 CH double bond C double bond CH and CH. Okay, this is the product form. Mechanism and all, I already have it. I already gave it to you. So this product which you'll get, this is called crotonaldehyde. Crotonaldehyde. Okay. Few basic points. Few basic things what we need to know is that rate will be dependent on aldehyde concentration as well as base concentration. Rate, because here also the hydrogen is being removed during the even CB mechanism. So rate will be more for hydrogen than deuterium than tritium. Okay. Uh, Usually, if the concentrated alkaline solution is being given, then reactions would happen faster and the rate will be slightly different in that case. Let me show you what are the steps that are happening. I'll write it in terms of steps 1 and 2, 1, 2, and 3. First step is CH2H with CHO in the presence of OH minus will become CH2 minus C double bond OH. This is called enolate ion. In this enolate ion, when you treat with uh, this is like step one, and this enolate ion when you treat with CH3 C double bond OH, from here it will attack, and that's how we will get this as CH3 CHO minus with CH2 and CHO. This is like step 2. Okay, and in step 2 we'll get an alkoxide ion, and finally to step 3, correct. uh, Well, up to this hydrolysis also, I'll write it as step 2. CH3, CHOH, and CH2, CHO. This is up to step 2. Finally, when the heat is being done here, to get this as CH3, CH double bond CH, this is done in 2 steps basically. First, you know, carb anion is formed because OH minus is a very weak leaving group. Then this will push to get this as CH3, CH double bond CH and CH. Okay. So that is how mainly in these 3 steps we are making the reaction to happen. Okay. Now, kinetics of the reaction depends upon how much is the concentration of the base. Got it? Usually it will follow second order, and this is the rate determining step. Clear? This is the rate determining step where we will 1 minute. Sorry, first one. This one or this one. These two becomes rate determining step depending upon what is the concentration we are using. Okay. Now what would happen here is, suppose if we take uh, mild OH minus, if you take mild OH minus, then you will see this first step would become the rate determining step. If you take concentrated OH minus, then this step would happen relatively faster, but this step will become the rate determining step. So I'll just write down this condition here. I'll put it here. Okay. This with dilute NaOH, and rate would be K into CH3 CHO square with OH minus with concentrated NaOH. So accordingly, you will fix out what will be the rate. Now, in this case, you will see because the hydrogen is being removed in the first case itself, this is what will happen. Slightly, if you go for concentrated cases, since second step is RDS, here hydrogen is not being removed. That's why the rate of hydrogen, deuterium, or tritium would be almost the same. Okay, this is what we need to understand. Now, given few questions, you should be able to figure out how the aldol works. Mainly here, it's all about solving the questions when it comes to aldol, how to solve various cases. That's it. So if I take 2 moles here, what is the product? Let me show you one case here. So what do? We will make this as double bond O minus with 1 mole and double bond O. Then you'll attack this one. And that's how subsequently you can make, and all here double bond O connected with this 6-membered ring like this with OH here, and it will undergo oxidation. It will, sorry, it will, on heating, you will notice this. It will make a double bond formation here. This is the final product form. Okay.
Sure. Sure.
Next, if you see,
So shouldn't the double bond form inside?
double bond form inside. No, but a double bond will always form as a conjugated part of C double bond O. Okay, so this should always be in conjugation. Yeah.
Okay, sir.
Next, if you notice the cross form of it, like if you have like this double bond O and H here plus HCHO, this is called crossed aldol. Crossed aldol, if you treat with OH minus here, then what do we get? First, we will get minus here, and that will react with CHO. Why? Because this does not have any alpha hydrogen. So aldol will happen only with respect to this one. So in that case, what is the product I will get? Because this will go and attack here. This minus charge will go and attack here. So I will get this as double bond O with CH2OH. Okay. And that when you heat it, so we will get double bond here with double bond O. So this is the final product form. Got it? And listen, whenever you have crossed form with an formaldehyde like that, then major product will be this one only. Do not write the major product as the self-aldol. Self-aldol will be very less in this case. Self-aldol will only happen when both of them will have, will be in a reasonable amount when both of them will have alpha hydrogens. Then self-aldol will be better. Got it? Next, suppose if the question is asked on the same terms, I'll ask you this question. No? So find okay number of uh, aldol and condensed aldol of CH3 CHO plus CH3 CH2 CHO. If we combine these two in the presence of base, what are all the aldols we can get, and condensed aldol, what do we get? You start with self here. Self, how do we do? First, write the structure the way it is, CH3. Then this CHO, you convert it like an alcohol. And then add the next CH2 again and put CHO. That's it. This is self. Same way CH3, CH2. Then CH, put this as CHO. And then CH3, CHO. This is again self of this compound self. Now let me put crossed. Okay. CH3, CHOH connecting from CH, CH3, CHO. This is cross. The last cross will be CH3, CH2, CHOH. And from the left, we will have CH2, CH. This is again a cross. Check out if there are any chiral centers here. So there is a chiral center here, chiral center here, chiral center here, 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 and here. So which makes it two compounds here, four here, four here, and two here. So total 12 different types of aldols are formed. Now taking these aldols and making into an alkene, that will become a condensed aldol. So condensed aldol will be CH3, CH double bond CH, CHO, and here CH3, CH2, CH double bond C, double bond C, CH3, CHO, and here CH3, CH double bond CH3, CHO. Lastly here CH3, CH2, CH double bond CH, CH. So again, if you notice, this will have cis and trans, so makes it 2, 2, 2, and 2. So total again 8. So 8 condensed aldol forms we can get. Okay. Can we expect Canizero if concentrated NaOH is given? Yes. You meant here, right? Here we can expect Canizero, and Canizero will be more preferred if the concentration of OH minus is increased. Okay. I hope all of you got an idea about how to do this. See the next one. Any cross aldol when you're writing, right, that is called as, Claisen-Schmidt reaction. So these are all Claisen-Schmidt reactions. In fact, cross aldols are all Claisen-Schmidt reactions. Nitro and cyanoaldol. Nitro and cyanoaldol, if you notice, basically here we'll have HCHO plus CH3CN in the presence of OH minus and followed by heat. So here we will have CH2 double bond CH and CN. So here this is how CH2 minus is forming, that is going and attacking first, and after that we are getting a double bond form. So that's how the reaction is taking place. Same logic goes to all other cases. So if you have PHCHO plus CH3Cl in the presence of OH minus and followed by heat here. So pH, CH double bond CH and cyanide. Instead of cyanide, we can also have nitro, so it will become nitroaldol. Okay, cyanoaldol or nitroaldol. Okay, next, suppose if you have pyridine with CH3 on this, and this is being treated with, HCHO here in the presence of OH minus. Here also you will notice that the CH2, here it will form CH2 minus, and that will go attack here. So what is the product I'll get? I'll get pyridinium here like this with CH double bond CH2. This is the product form on heating. Okay. So if at all we have any strong withdrawing groups on this end on benzene group, then it can definitely form an enolate kind of a structure here. So we'll get this as CH double bond CH2 with NO. This kind of product is observed. Okay. Lastly, suppose if you have 8-membered ring like this, we have 3 double bonds here and then one OH group here. Sorry, to get this product, suppose I have CH3, CH double bond CH and CHO group is here, and I have same molecule again, CH3, CH double bond CH and CHO here. Okay, so you can expect like this molecule attacking here, this molecule attacking. Okay, as it attacks in the presence of OH minus, we will get a cyclic structure here of 8-membered ring like this, with here getting a double bond already existing with OH and OH forming. Okay, OH and OH forming here, and this, if you treat with OH minus here to make a condensation, you know that elimination will happen, OH and H will go, double bond will form. You'll get double bond, double bond, double bond, and OH. Okay, clear? And again, if I make, sorry, this is on heating. This is on heating. Again, if at all I start heating it further, this time double bond will form there, but the structures will completely change into a tub shape. So that's how cyclooctatetraene is being made. Okay. So I suppose this part is clear to everyone, right? Next, intramolecular aldol, if you notice, intramolecular aldol. So that includes CH3, C double bond O, CH2, CH2, CHO in the presence of OH minus. I can get C2 products. One is a 3-membered ring like this with OH. The other one is a 5-membered ring, OH and double bond. Okay. So where I'm getting a 5-membered ring will always be more stable. So ring stability, if you notice, it should always be 6 greater than 5, greater than 7, greater than 4, greater than 3. Always follow this order. So whenever it is forming, what is the ring structure, you will have to notice this. Okay. In this case, just mention from where to where the reaction is happening. Okay. So 1, 2, 3, 4, 5, 6. These are all examples. 1, 2, 3, 4, 5, 6. I have a double bond O here and a double bond O here. Okay. So which means definitely attack will happen from here to here. This arrow you should understand from where the attack is happening. Next again 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Right. So here we have a double bond O and here I have a double bond. Okay. So then attack would happen from this end to this end 1, 2, 3, 4, 5, 6, 7. Okay. And we have 1, 2, 3, 4, 5. So which one is more preferable? 5 is more preferable like this. Got it? Similarly, if you have benzene having an aldehyde here and then double bond O, CH3 is there. So again from here to here the ring closure will happen. Okay. Similarly, if you have double bond O, double bond O here, usually this comes in ozonolysis. In this case also, you will take this and close it here. And while closing, you see the ring says 1, 2, 3, 4, 5, 6, 7. One will be 7-membered ring, the other one will be 5-membered ring. Like this way. And the other one will be 5-membered ring like this. Okay. Where it got connected here, so there we will have OH and here we'll have a double bond O, which on heating typically will become a double bond here and double bond. Okay. This is how it will happen. Next one is a retroaldol cases. Retroaldol cases is going from one aldehyde towards the other aldehyde. For example, if aldehyde is already given like this, double bond, aldol is already given like this aldol is given. And you treat that in the presence of OH minus and heat. Okay. You basically open the ring and go towards the other side of it. Okay. So if you open the ring, first, see, even this will not be given. Sorry, first this will be given. So first always try to write the alcohol part of it. OH will be given here like this. And then try to break the bond because where the alcohol is formed, possibly that is where the connection has established. So from here, if you take from this carbon onwards, you start making a straight chain. So here we have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And this end, one end we have a double bond OH on which the attack has happened. The other end we had a double bond OH. That's how the attack has happened here. So this is on the retro side. Now what you do, instead of attacking from this end now, from the third position only you attack. The third position only if you attack from here to here, we'll get another type of aldol. And this time the aldol will be like this, a 3-membered ring with double bond O with OH, right? And this on heating, we will get double bond here with double bond O here. So even if the question is given this one, you will have to go towards this side. If the question is given this one, you'll have to go towards this side. So depending upon which direction you're going. It is not about stability. Retroaldol is all about showing that two aldehydes can coexist. So two aldols can coexist. Okay. Next. Notice it when you have acid catalyzed aldols. Acid catalyzed aldol reactions. So if I take 2 moles of CH3CHO and I take H plus and heat, we will get this as CH3, CH, CH, CH. Here also exactly same products. Slightly mechanism is different. First we will have tautomerism form and then elimination usually happens via even mechanism. Most of the time, it is even mechanism. I am directly writing the reactions which are important here. First reaction being ketones. Ketone, when you treat with HCl and heat, and it depends upon how many moles I'm taking. If at all I take 2 moles here, I will get double bond CH, C double bond OCH. Okay, this is called mesitylene. This is called mesitylene. Okay. Now imagine if at all I take the same compound double bond here and make
It
one
is
more
a mixture
reaction
option.
with what beta? Yes? No. If I write again here, so we will get double bond CH, C double bond. And this side also we will get keto attached. Now this one is called forone. Please remember the names. These are directly name-based questions asked. Forone and mesitylene. Okay. So if the 2 moles are given, you will stop here. If the 3 moles are given, you will stop at forone. Second case, if you have 3 moles of ketones given, C double bond of CH. Yes, beta.
Another. Is it a mixture option?
Huh? Can you repeat?
So the above one is mixture option.
Mesityle oxide. Sorry, sorry. Yeah. Mesityle oxide, not mesityle. Yeah. Thank you. See, lost the screen. Reshare. Now, this reaction, when you treat with concentrated H2SO4, then only it will happen where you will have complete benzene forming, and this is mesitylene. This is mesitylene. Okay. Do not worry about mechanism and all. Here, it's more about knowing the idea about how to get the products done. Okay. So, guys, these are the aldol cases. Mostly, these are the ones which are asked. Next, KCP versus TCP cases. Okay. So, what is the reaction that will happen in terms of KCP and TCP? See, what we are trying to understand here is when you have a very strong base and you are pushing that towards, uh, group like this, ketone here, then whether you treat with OH minus here or whether you treat with LDA. LDA is a very, very strong base. This is the structure minus and lithium plus. Now, in both cases, because it is symmetrical, we will have minus formed here, which will be conjugated as alkoxide ion like this. Okay. Or if at all we have any difference here, like methyl is given here, OH minus, which is a normal base. A simple base or a normal base will always go for more stable enolate ion like this, O minus and this. This is more stable enolate ion. Okay. While if you take LDA, then it will always go on to more stable carbanion. Carbanion. So if you are always going for more stable enolate ion, it is called TCP, thermodynamically controlled product. If you are going for more stable carbanion, that means it is KCP, that is kinetically driven product. So remember the difference when we have to take for TCP and when we have to take it for KCP. Okay. For example, what are the questions that are asked? Directly we'll check out that. Suppose this is how the question has been framed. Double bond O and there is a methyl given. And I gave you LDA at minus 78 degrees centigrade followed by CH3I followed by CH3I. Then what is the product we will write? Because LDA is a strong base, it would prefer to give more KCP product. So we will get minus charge here and that minus will connect onto methyl. What is the product you will get? You will get this as double bond O. One methyl is already there and one more methyl will come to a bond. These are the two methyls which you will get. So similar lines, if we add it onto one more product, suppose if you have a double bond and two groups here, and check if I treat with first NaOH followed by CH3I. So what is the product you will get? The double bond O. Now, since there is no alpha hydrogen here, that is the reason why you'll get anion here, and that will also connect with this CH3 and you'll get it. So whenever there is an option of alpha hydrogen, you should go for more stable in the case of NaOH and more stable anion in the case of LDA. I guess this part is clear. Okay. Next. Halogenation. Halogenation. Halogenation of alpha positions. So if on alpha positions, if you do halogenation, what are the products you will get? So first, if you take ketone, react that with X2 in the presence of NaOH. That is in basic medium. In the basic medium, if you put it, then you will notice it will become this product, halo, and this is called haloform reaction. But if you do the same thing in acidic medium, that is X2 in the presence of H2O or you know H plus in the presence of X2 here, in that case, you will notice that only one halogen substitute has been observed like this. If you take 2 moles, you'll get one more halogen here. Okay, so that is only if you follow the reaction again. If you follow the reaction again, you will get X here and X here. Okay. Again, you will not be asked too much of reasons for it. My suggestion is just remember what happens in acidic medium and what happens in basic medium. Guys, clear? Suppose if you are given like this, double bond O, and we have been given Br2 in NaOH, or I gave you Br2 in CH3COOH. In this case, you will add products with two bromines both sides here, while here we'll add only one bromine, considering it is excess. This is in excess. This is the product you will write. So can you explain H plus and X2? Mechanism wise, it works like this. I'll take this example here. OH plus was because it is an acidic medium. Okay. And you will see that once you get this, this will have sufficiently positive charge. So this one will also start becoming slightly acidic in nature. Okay. Now, as it starts becoming slightly acidic, in acid case here, if you recall, water itself will take away this H plus and try to prepare an enol form. Your first step should be always about formation of enol. Once you get enol, the halogens will get attacked by the pi bond here, and we shall get this as OH with positive charge and Br. The lone pair will close it here. We will get this as double bond and Br. So this is like the alpha substitution which you will get. Satvik, clear it up?
Understood, sir.
Right. Rest of the mechanism, how it happens, I've already given you the notes. I suggest you just follow that once. Okay. Right. Last reaction is about Perkins reaction. So one important application in terms of aldol, which are in a similar lines of aldol, is Perkins reaction. Perkins reaction usually is observed whenever there is a benzaldehyde form. So if we take benzaldehyde and treat that with anhydride, CH3, C double bond O, C double bond O, CH3. So if you are taking this anhydride, you will take the same base, that is CH3CO minus Na plus, and heat it. In that case, what we will notice is that we will get cinnamic acid and acetic acid. These are the product form. Of course, it is followed by via right now that also is followed via hydrolysis. H3O plus has been added, then only it will become cinnamic acid. I hope this reaction is clear. Again, mechanism based question was asked to you during the working, and I discussed it recently. If you recall, last month when we had this topic, then the mechanism has come. It is in the notes. If you want it, just follow that once. I don't think usually it will not be asked about what is the mechanism, but you just need to know the product, how it is coming. Okay. And next, reaction with HNO2. Reaction with HNO2. HNO2 reaction is nitroso substitution. That is, if you have a double bond O here, and let's say I treat it with NaNO2 in the presence of HCl. Basically, it is generating HNO2, and HNO2 will give us N double bond O substitution. Basically, we can write that in the form of oxime. It's double bond N and OH. This is the oxime form which we can write. Okay. This is the product which is formed. I'll directly take you through an example that was asked in JE once. So this was the example which was asked. Like I started with acetone, treated off with NaNO2 and HCl. Then I got a compound X. And this compound X, if you treat this with anhydride and heat it, we got compound Y. And this Y, when you heat it with H3O plus, I get a compound Z. And Z, If you treat with concentrated H2SO4 followed by H3O plus and heat, we'll get A plus B plus C. Find all of this compounds. Okay. Notice it. What are the compounds I can get? First, X is the nitroso group. So we will get here as NO is the first one. Okay. And in nitroso, when we are using, I can always write this nitroso in the form of oxime. Just now to discuss that, we got as double bond with double bond N and OH. And in the presence of anhydride, it is like formation of OAC here. OAC is a good leaving group and hydrogen is present here. So on heating, dehydration will take place. So what do I get? Double bond O with triple bond N, removing out that water. And on hydrolysis, you know that cyanide hydrolysis will always give you acids. So we will get this as double bond O and OH. So we will get this as an acid plus ammonia, acid plus ammonia. And then acids, this is alpha, this is that alpha carboxylic acid here. And if you recall, when we heat that in the presence of H2SO4, the other day I gave you that. That one is we will get acid here on this position, and the central carbon will come out as CO, and the other one will be H2O. So these are those three products: A, B, and C. I guess this part is clear, everyone. Right. Okay, guys, we'll stop it here.